Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Shielding from the Dark Side of the EMI Force. Identify and contain noise at source using housing, grounding, and PCB solutions. Our speaker is Mohamed Al-Alami. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the link to the presentation in the next few days, and the recording will be available at our website shortly. Now I will hand over to our speaker, and I wish you an exciting presentation.
Here we go. Super. Good morning, everyone. Thank you for joining this webinar today on shielding from the dark side of the EMI Force. And those Star Wars fans out there will understand the theme behind this presentation today. And those poor EMI engineers or EMC engineers who have had to spend hours in an EMC lab will also hopefully understand what the topic is about. So without any further ado, let me just explain the basics of what we're going to cover today. We're going to look at some basics of electromagnetic shielding, just a bit of an understanding of certain concepts. We're not going to elaborate that too much as we have got very limited time today. And then we will look into shielding solutions. And in doing so, we're not just going to talk about these solutions. We're going to show you demonstrations of these solutions, which hopefully will give you a better understanding of how this actually works. So let me just, minimize this. That's better. From a shielding solution, we would look at two main aspects or two main types, the housing type solutions and the board level solutions. There are others, but we will concentrate on these for today. So we're starting off with looking at the impact of electromagnetic fields from a radiated point of view, received, of course, by conductive structures. Everything within an electronics unit could be a conductor, receiving or radiating, or susceptible to external radiated field from cabling and harnesses associated with your unit or surrounding your unit, interfaces, apertures. All of these can act as antennas, and these antennas can pick up noise or can radiate noise. Same thing from a PCB, so internal to your unit, your tracks and layout and ground planes, and any slots or slits that you have got in the PCB can also be a potential source of noise. And finally, of course, we do not forget about our components, magnetic components, particular things like transformers, can also radiate magnetic fields, integrated circuits as well, electric field predominantly, heat sinks, sort of metal structures that can also act as radiators of that noise. So the importance of what we're talking about here is trying to identify these as potential noise sources. And once we identify that, then we can look into how we can implement solutions. And as you can see, this can be fairly painful exercise, trying to figure out where the noise is coming from, particularly, of course, when it is radiated. Conducted, relatively simpler. Radiated, it gets a bit more complicated. And so does the solution, hence today's presentation. Moving on. Another basic we will start off, or the first basic I should say we will start off with, is wavelength. Very simple concept. I've got the relationship here between wavelength and frequency. And the idea behind this is, again, to take you a step closer into identifying that noise source. When you're sat in that EMC labs, twiddling your thumbs, scratching your head, trying to figure out where am I getting that 74 megahertz problem. This is something that can be quite useful in trying to home in onto, is it this cable harness, or is it an internal harness within my unit, or is it a track on the PCB, or is it an opening or an aperture in my unit that is radiating this noise out. And the relationship between frequency and wavelength is what gives us an idea based on that length of that wavelength as to what the actual length of the cable harness, etc., or the track on the PCB is. Hence, what could be the source of my noise. And once I've identified that, then the next step is to try to look at implementing solutions. All right, this is a bit of a scary diagram when you first look at it, but this is also quite a useful concept here. And I'm not expecting naturally for you to start plotting curves like this or using curves like this to identify your noise source. But the idea behind this is just to clarify a basic concept of wave impedance. So if you look on the left-hand side, and I'll just pull up my marker, my laser pointer. So on the left-hand side, and I'm not sure if it doesn't look like my laser pointer is working for whatever reason, but it doesn't matter. On the y-axis, I can talk you through it. On the y-axis, we have got impedance in ohms, and this is the wave impedance. And as you can see, for an electric dipole, the green curve, it's a high impedance type field. While if it's a magnetic dipole, is the source of my noise, that's a low impedance type field. Where? In the near field. So in close proximity on the x-axis is that distance from that noise source, and that's normalized to lambda over 2. Lambda is the wavelength. I should have mentioned that on the previous slides, so I do apologize. So in the near field, this is what these magnetic and electric field behaviors are like from a wave impedance point of view. So the electric field is high impedance, and what we want to do is we want to mismatch this radiator, this antenna, this cable, this harness, this track, and so on. So how do we mismatch it? We need to introduce a low impedance. That's what you see in the picture that I've introduced there. What we're trying to do is between those two plates that you see with positive and negative charges, we want to equalize those. We want to balance those. So in Star Wars terms, we want to bring balance back to the Force. And you will see me later on show you how we can do this as well using our shielding components. So that's a very important concept, this mismatching of the impedance. You're forcing this. We're not an RF circuit now. We are a noisy EMI source, and we want to attenuate that noise. And the same concept we follow from a magnetic point of view, in that we introduce high impedance material so that it can absorb or reflect back, could also be low impedance, that magnetic field, so we do not feel the effects of it. So that covers another basic concept. Moving on, we'll finish off from a basics point of view on shielding apertures. And apertures or openings in a unit or in a shielding can, like you will see me talking about later, sometimes are necessary, predominantly from a heating, of course, point of view, so that they can release some of that temperature rise in the component or in that particular circuit that you are shielding with a cabinet. Or from, of course, a fan cooling point of view. Now, the impact of introducing these apertures and openings is big, and when it comes to affecting the shielding attenuation. And what I thought to put in here is just to show you the impact of that via this equation. So the attenuation of an aperture with multiple different holes through it is reliant on the number of holes, and that would be the maximum number of holes in any dimensions, so in the X or in the Y or diagonally, multiplied by, as you could see from the equation, also proportional to lambda wavelength, as well as the biggest diameter of that hole, which is the diameter of the hole in the case of a circle. Another basic concept that we've also got in here is the maximum slit length to allow you for 20 dBs attenuation. So if you want to achieve a minimum out of your shield of a 20 dB attenuation, and you need to have a slot there or an opening. So that shows you the frequency behavior. And as you can see from a frequency behavior point of view, you have got a maximum slot length of 50 centimeters to achieve a minimum of, or a maximum, a minimum of 20 dBs attenuation, I should say, at 30 megahertz. So you can see that, of course, there is that relationship with frequency as shown on the previous slide with wavelength. And another also important point to keep in the back of the mind is the number of these. The more apertures or openings that you have, the more there is a degradation that you will see in that attenuation, as per the equation again that we've seen before. 2 instead of 1 will give you a 3 dBs drop in attenuation. 4 holes or openings will give you a 6 dBs drop in attenuation, and so on and so forth. So this is a very simple point. You know, if at 30 megahertz, I've got a slot of 30 centimeters, say, I've got 20 dBs attenuation. If I use 2 of these, I drop that by 3 dBs. So that's as simple as you can put it. And the previous equations shows you that concept. Okay. So let's move on to shielding solutions. And on this page, it's a nice summary page. It shows you quite a wide range of different solutions that we have as Würth Electronics, and we can provide you. There's a lot that we can offer on various different locations of your unit. And that's what I like about this diagram. It shows you where things can go. We naturally don't have enough time to go through this. I'll take probably half a day at least in order to give you a full picture of each and every one of these. We are going to select a few important shielding solutions. We will, as I said before, we'll look at housing predominantly and PCB based, and we will look at those in a bit more detail for you. All right, let's start off with casing joints or enclosure solutions. So from an enclosure point of view, before we look at the solutions itself, it's a conductive structure, of course. From an enclosure point of view, that's what we're looking at. So with that enclosure, we have got seams, we have got openings, we have got edges, we have got apertures, and these apertures are what we need to make sure that we are covered. We have made sure that we have got continuity there, because if we don't, what we end up with is an issue from a magnetic, from an electric field, as you can see from the picture here, causing our electromagnetic field and high impedance fields, as we have shown before. So how do we bring balance back to this force? We introduce shielding gasket material. And shielding gasket material, excuse me, what shielding gasket material allows you to do is bring that balance the charges across those two faces, the cover and the enclosure of the material. And it does not necessarily have to be the cover of the material. It could be an opening like this D sub 9 that you see. We can shape a gasket to that shape of that unit to make sure that we close completely the opening as you're introducing the actual connector into the unit. And these types of gaskets, quite a wide range. We will talk about today 2 types, conductive fabric gasket and the spring contact strip gasket. There's quite a few ranges of these, as I mentioned before, with various different properties. So starting off with the conductive fabric gasket, this is a foam-based material. That's what you see on the picture on the right-hand side. That foam material is surrounded by a fabric which is impregnated with a nickel copper conductive material. On the back side of this conductive tape, there is an adhesive tape, and that adhesive tape can be conductive or it might not be conductive as well. There's options there that we can provide. By the way, with these components, they're very customizable, so we can easily customize this to the length or the shape that you are looking for. They are IP54 rated, and they are also UL94V0 flammability rated. One key feature of these is they have got various different profiles, as the pictures down at the bottom of the screen show. Now, with these different profiles, they've got the huge advantage of fitting within the size of the unit or the aperture that you have. So it gives you that ability to meet 2 surfaces, not necessarily just the lid and the actual body of the enclosure, but any 2 surfaces internal can be met together. So that's one main advantage of this. One thing to watch out for when you are selecting this type of gasket is the base material of your unit, because there's something called galvanic corrosion, which, as you can see in the picture, can cause issues from a corrosion point of view of your material. So for example, if your base material for your enclosure is aluminium, it would be best to use an aluminium fabric material. So the nickel copper that we talked about before could be made with aluminium. We have got two types of conductive material based on your enclosure. On the next slide, we will look at a video by my colleague Laurent Foucault, who talks to us a bit more about the gasket material and how useful that is in terms of a practical example.
Hello, my dear friends of electronics. Today in this video, I want to show you the effectivity of shielding gasket. What we have here a small box. It's an EMC box from Virtual Electronics in collaboration with the University of Valencia, with the Cathedra EMC. And it's inside a small signal generator, which is generating a quite noisy signal, closed on a 50 ohm resistor. And then we have here a spectrum analyzer and scanning from 100 kilohertz up to 400 megahertz. Near field scanner probe for magnetic field. So I will switch on the trace and put the maximum hold, and I will go on the corner, and then you can see it is on the corner. It's a metal box, aluminum metal box, completely closed and strongly closed with the screws. But still, if you go here, you can see, oh my God, there are coming some really big noise peaks outside. So this is the maximum peak. So now I will put that in memory, open a new trace and put maximum hold as well. And off the other side corner, again, I will go on the cell corner and look what happened. Now you can see here is a big difference. Why? Because this side is metal, this side is metal, here's all the screws closed, here are the screws closed. What could be inside in this box? Maybe I should show you the trick. Ta-da! Like you can see on this side is no gasket at all, and here we use a conductive gasket, WELT. This gasket makes that your shielding effectivity is much better, and you will have no noise coming out of the box like you can see in the machinery, and hope you enjoy it.
So there you go. There's Laurent showing us that LT material, the fabric material in practice. And another type of option that can be used on things, and you probably have seen this in EMC chamber doors and enclosures, is this spring contact strips. Copper, beryllium, or stainless steel, two different types of materials that we have, and naturally with this as well, customizable to the requirements of the customer. So this is another option as well from a shielding gasket point of view. A final option that we will look at as well is another type of material, which is rubber-based with a conductive filler. This is an elastomer-type gasket. It's an IP68 rated. This is one of its main advantages. The fact that you've got, of course, full protection from dust and water under pressure from a protection point of view, from a rating point of view. So this is another also type of gasket material that can be quite useful. I've included a nice summary table here just to give you a general overview of the various different solutions that Würth have from a gasket point of view. This is not everything, by the way. We have also got more other than this, but this is just to compare these specific type of gaskets here from an ingress protection and rating point of view, compression force, which we mentioned for all of our gasket as to what the optimum, maximum, and minimum compression forces are. And we also look at the attachment methods available as well as the operating temperature. So this just gives you a nice summary of these various different shielding materials options. Now we shift attention towards board level shielding. And we start off with the shielding cabinets or shielding cans as they're known. And with the idea behind this, of course, is that sometimes you have got either sensitive or noisy. So you're not necessarily shielding something that is just radiating. You also could be shielding a circuit that could be susceptible to noise from an external source. So in this case, you can use a shielding can. And as you can see here, we've got lots of openings and apertures in that shielding can, and that would be reducing its effectiveness. But however, of course, with careful design, you can make sure that that does not impact your functionality. And that is still giving you decent shielding is what I'm trying to say. So with that side of things, it's very important, of course, to identify the fact that with a shielding can, it's got 4 sides. That's not a Faraday cage yet. You will need to, of course, stitch that down to a ground plane internal to your PCB to make your full Faraday cage so that you have got the full effectivity of that shield as a connector, as a low impedance connection down to ground. And that being the case, it will give you the full benefits of that attenuation from a shielding point of view. Let's look at what available options do we have. From a component point of view, we have got a one-piece solution or a two-piece solution. So one piece could be just a component that you actually place surface mounted through hole on the board, or you can have a frame and a cover. Another type of solution is a customized solution, and this is something that we can do very easily with these types of components, the shielding cabinets. We can customize an internal wall so that you can separate 2 different types of circuits within that wall structure. So as you can see on the bottom right-hand side of the picture, we have got an internal chambers or 2 internal chambers. We also have an option for what's called an SMT clip, which you will see also Laurent present in a couple of slides down, where he's looking at a demonstration as well for you. And with that, what we can do is just easily and simply surface mount, solder these on the board and fit the actual cover on top of that to make life simpler and easier. And the cover will fit in the sides of the clip. So that's the standard type of shielding gasket. We also have another type of shielding gasket, which we call the seamless shielding gasket. Now, this is produced in a different production process called the deep drawing production. And the idea behind this, as you can see from the picture, there are no seams for this. This is a fully enclosed, contained, almost pressed type of metal enclosure. You'll have the frame as well as the cover. As you can see, you can pick and place the frame as well. And the idea behind this is, as you can see in the picture, it gives you a much higher or wider range of attenuation beyond 60 gigahertz. So applications like 5G, IoT nowadays, GNSS, and so on, this would be the more suitable type of shielding cabinet compared to the standard part, which we have been talking about, which is metal folded 4 sides shielding cabinet. So again, with the availability or the option now of going much higher frequencies, this type of component is the more suitable one from a shielding point of view. I finish off with a little what we call shield DIY kit. It's an A5 sheet of nickel silver type material. That's what it's made up of, with a 5mm grid on it. So you can make your own DIY little shield in your office and test it out. You can use the clips that I mentioned before to create that shield. Laurent will show us how this is done and how effective this can be from a noise point of view on the next presentation.
From your shield D, which you can see in my previous videos, I did present this homemade. You can do your own cabinets by yourself, and we will put this shield D on antenna, which we will source from a small generator. You make a kind of rectangle signal. It's a small quartz generator here. Make oscillation and put the signal to this antenna. And in the same PCB, we can put and solder this cabinet, which I prepared before. It is right now soldered. Or when you make mass production, you have the possibility to use that kind of frame. Solder the frame by pick and place, SMD, and you have the cabinet to close it, and you can re-access for some tuning your device, or if you want to access again your electronic. But if you don't need to access your electronic, you can save some money, and you can use the easiest version, which is just a cabinet which can be soldered by pick and place SMD, and then it's done and you have a completely shielding. So first, now we'll switch on our noise generator. which I'm connected to the battery pack. And then we have a small sniffer. This is a sniffer made from Universitat Valencia in collaboration with Ultra-Electronic EMC Cathedra. And this one will have also power from the USB. And then we have a magnetic field, near field sensor. And if I go close to this antenna, you can see on the LED and you can hear it make magnetic field sniffering. Now I will take this small build own cabinet, and we have some clips, special clips which can be placed on pick and place machine with SMD, and I will try to fix it in the right way to have a good connection. That's it. And now again with the antenna. You can see it's not working, and if I go to the septum, exactly where the signal is coming out, you can see here, but
Great. So nice and clean, as we can see, shielding effectiveness for you. Now, I'll finish off today with looking at different types of shielding. Still can be considered also board level shielding or housing shielding. It's a very flexible shielding. It's called a flexible absorber sheet or absorption sheet. This type of material is a magnetic type material impregnated within a rubber base, which gives it that level of flexibility. And the idea behind this is a very effective type solution, particularly, of course, for magnetic type material, hence it's magnetic type impregnated grains within that rubber. So it gives you something called reflection and something called absorption. The fact that it has got an adhesive backing, the fact that it is non-conductive, is magnetic, you can stick it anywhere within your PCB enclosure, within your enclosure, as you can see here. And it can be very effective in absorbing or reflecting noise, as the picture shows. So on the next slide here, I'm just showing you some of the key characteristics of this type of material. Here you can see that we, as Würth Electronics, do various different grades of material. We give them numbers here. And these materials are characterized by two main types of parameters, something called the mu dash, which is permeability, which is the real permeability, I should say, which we call also the reflective permeability. There is the mu double dash, which is the complex side of that permeability, which is the absorption, which is the attenuation side. That's why you see two curves per material. So you get the mu dash, that's the permeability in gray, and the mu double dash, which is the absorption side of things, which is the attenuation side of things. So it gives you both, and both effects are useful from an EMI point of view. Okay. Let's also look at another aspect of this, selecting a specific thickness, and these come in various different thicknesses. We'll talk about thickness impact on the next slide. Let's look at how much attenuation this material gives me. So you will see we have also got OnRed Expert, our flagship selection tool, a very nice way of indicating for you how much attenuation you're going to get out of each one of these materials. Because permeability, which we showed on the previous slide, is not really a clear indicator of what is the actual dBs in terms of attenuation that you're going to get. So we've done a little test, as the picture shows you here, that shows you how much impedance you're going to get out of this type of material. You can also, as you can see here, implement this not necessarily on housing only, but actually directly onto bus lines, on noisy tracks on the PCB, and achieve some good attenuation as well. I'll finish off on this type of material by showing you the impact of the thickness. So this is one grade of material, so it's the same permeability across the board here. But what you're seeing is the variation of impedance, attenuation, same thing, versus frequency for different thicknesses, from 0.1 of a millimeter all the way up to 1 millimeter. And you can clearly see the thicker, the better. Not necessarily across the whole range. You can see that things do flip and change as you go up into the 7 and 8 gigahertz, beg your pardon, range. But in general, the higher the thickness, the better, at least in the usual ranges up to maybe 4 or 5 gigahertz.
In this video, I want to show you the effectivity.
Here is Laurent talking to us a little bit about the impact of these types of shielding flexible absorber sheets. I will include a link to this video for you to have a look through later on. I'm just concerned, I'm watchful of the time, so I want to finish off a couple more slides. So I will leave this video for the audience to review at a later stage. And I will include the link for it, like I mentioned. So shielding, this is another type of flexible shielding material with a twist. So this gives you the same performance as a flexible absorber sheet in terms of the fact that it does attenuate radiated field, but it also has got this ability of having a very good heat conduction, very low thermal resistance. So it gives you both aspects of things. And the idea behind this is, as per the picture shown, gives you an idea of the application here, is if you have got a noisy processor with a heatsink on top, then the heatsink becomes noisy itself. It becomes the antenna, which is much bigger and capable of radiating further. So what you can do is introduce this thermal flexible absorber sheet material in between, which allows you the capability to attenuate the noise and at the same time maintain good thermal performance for that microprocessor, so it doesn't overheat, in other words. The last section we will talk about is grounding point of view, so board level shielding again, but from a grounding point of view, and this is in the form of specifically what we call contact springs. Now these are copper beryllium or phosphor bronze based as a metal with a plating of gold, nickel, or tin. These are very reliable, and hence why we say watch out, because there are lots on the market on this. You need to watch out for the reliability of this and the plating and the thickness of the plating of this material to get the most out of its performance. The idea behind this is you maintain grounding between a board, as you can see in front of you, onto another board or onto the side of the enclosure, so you have got a good grounding all around, or ground connectivity from one board to another, to the chassis, to the actual enclosure. Another point to mention on this is excessive compression. So we have designed, or we have got components that are special designs that can avoid this excessive compression. So it's got a compression security system. So in case you have got an overly stressed or compressed part, it wouldn't get damaged by the inclusion of this clever design or mechanical design of this part. So it gives you that extra feature. And finally, on this side of things, we mentioned this is very useful from a grounding point of view, but it doesn't necessarily have to be used for grounding. This can be quite useful as well from a connectivity of a signal point of view, particularly things like RF circuits, or even power grounding, power side of things as well, power and signal side of things. So this is also an option there for connectivity there. I'll finish off with a final part that is very similar, I guess, to that shielding or the contact fingers we've just been talking about, but this is a foam-based material. This is very, very similar to what we started off with today, which is that foam fabric material. But instead of it being a fabric, it's tin-plated on the outside, foam in the middle. It's called a cellular block. So you can pick and place this, put it on a PCB, and solder it, as you can see there. And it's compressible. You can compress it, as you can see, to get good conductivity and connectivity between two surfaces. So this gives you another option in terms of, or alternative in terms of making contact between two boards. Okay. I have included a final few web links here for your information, which I'm hoping you will find useful. Some of them are application notes. I've also included the RedXpert link to that magnetic shielding material I mentioned before. I hope you find this quite useful in terms of trying to select the suitable components and parts for your future designs. And on that point, I say thank you very much for your attention. I do apologize if I have run over for a little bit, and any questions are welcome. Please fire away.
Thank you, Mo, for your interesting presentation, and may the force be with you.
Thank you.
Now I think we would like to turn our attention to the questions. So maybe just the first question. How much attenuation does the flexible sheet provide?
Okay. So the attenuation of the flexible absorber sheet in dBs is very much dependent or reliant on the frequency that you are looking at. And this is why I was saying earlier, RedExpert is a fantastic tool in that. I might be able to even show you on RedExpert itself. If we can look into, yeah, there we go. So from a magnetic shielding material point of view, let me just show you my screen again. And we can see here, we have got the permeabilities that I was talking to you about versus frequency, but we also have got the curves that show you the performance in terms of attenuation versus frequency. And you can use cursors to cut across to your frequency of problem, and you can see how much attenuation you're getting out of that particular component. And that's where it can be quite useful. You can then have drop down or select based on ascending and descending. You can get 17 dBs at that 533 megahertz frequency I've selected out of this type of material. So that's where sort of attenuation side of things in simple terms is a function of frequency, and you can see this in RedExpert. I hope that answers the question.
I think so. So just going on with the other questions. To what extent of vibration and shock levels and types SMT clips are resistant?
That's a good question. Now they are tested under vibration, and we can find out that exact specific data if you're looking for it, but that will also depend on, I guess, the location within your board itself and what sort of level of vibration and mechanical strains that might see. I mentioned that we do have this higher level of compression part or excessive compression part. That's naturally from an operating point of view, as it's compressed down when you place it on top of another PCB or place another PCB on top of it. But from sort of a standard level of vibration, they all go through the standard levels of vibration. If my memory serves me right, I think it's 5G, but we can check this specific number and get back to you. So, but again, I say with this because based on previous experience with vibration, this is very much reliant on where it sits on your board itself, because you will have various different levels of vibrations as you put your component or your board on a shaker or your unit on a shaker. You will see various different resonances within the board. So this might impact its ability, of course, but from a testing point of view, from a capability of a part point of view, I believe it's, I think, 5G, but I can confirm that to you if you leave your email and details when we'll get back to you on this.
Okay, thank you. So we have still some questions left, but we are a bit over time, so we will answer them after the presentation via email. Thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is Transformer Design for EMC, Practical Construction Techniques. So, and the presentation starts at 11. See you there and enjoy our digital days.
Thank you.
Goodbye.